Hi students, today we are going to derive ideal gas equation in the chapter Heat and Thermodynamics. Now in the lower classes you must have studied Boyle's law, Charles' law and Gay-Lussac's law, is it not? Let us begin from Boyle's law. So according to Boyle's law, at constant temperature, the volume of a gas is inversely proportional to the pressure applied on it. So, at constant temperature, this is the beginning of Boyle's law. At a constant temperature, volume of a certain mass of a gas is inversely proportional to the pressure exerted on it. Okay, now what is Charles' law then? You have studied Charles' law. Charles' law begins with what? The statement begins with what? At constant pressure. Is it not? So, this is at constant pressure. Again, the volume of a gas is directly proportional to the absolute temperature. The T is the absolute temperature in Kelvin scale. Now, I am going to combine Boyle's law and Charles' law, because both V is on the left hand side. So I can write from these two, V is proportional to T by P, or PV is proportional to T, or PV is equal to a constant C multiplied by T. So this is the first equation. So here C is a proportionality constant, which is a positive constant. So we can write C is a constant. But once again, this constant depends on the number of molecules present in a gas. So in a container, there are so many number of gas molecules, is it not? So this constant is once again is equal to, or it is first proportional to the number of molecules N present in the container, or C is equal to some other constant K into N, where this K is called Boltzmann constant. So Boltzmann is the name of a physicist, and he has given the value of this constant, and the value is found to be equal to 1.38 into 10 to the power of 23 minus 23 joule per Kelvin. Okay, and what is capital N? This is the total number of particles. Okay, number of particles present inside the container. Okay, so in place of this positive constant, what shall be substituted? It is also equal to another constant K times the number of particles. So instead of C, I am going to substitute K into N. Therefore, now I can substitute P into V is also equal to N times K into T. This is another very important equation required for solving the numerical problems. Okay, so this is the basic form of the ideal gas equation. P into V is equal to capital N times K into T, where K is called the Boltzmann constant and N is called the number of molecules or number of particles present in the gas. Okay, you must have studied a concept called as Avogadro's hypothesis, is it not? 1 mole of any substance contains the same number of molecules. That number is called as Avogadro number. Therefore, I can express the total number of molecules in terms of Avogadro number. So, the total number of molecules must be equal to some number mu, number of moles, times Avogadro number. So, here Na is equal to what? 6.023 into 10 to the power of 23. This number only is called as Avogadro number. Okay, Avogadro number. And what is this? Mu is called as the number of moles. Number of moles. So the total number of molecules in a container can be expressed in terms of number of moles and the Avogadro number. Therefore, in place of this n, what shall be substituted is mu times Na. Is it not? So once again, the second equation takes a new form. Okay. Therefore, P into V is also equal to, in place of n, mu into Na. So this is mu into Na into remaining factors k into T. Okay. K into T is there. Now, this product Na into K, so the product of Avogadro number and Boltzmann constant, the value of one constant into another constant, is it not? That must be some other constant. That constant is denoted by the symbol capital R, and that is called as gas constant. So this is only called as gas constant, or sometimes it is called as universal gas constant, because its value remains the same for all gases. Understand? So in place of the product Na into K, what shall be substituted is the gas constant R. Therefore, now the above equation takes a new form. P into V is equal to mu times R into T. Okay. So this is the final equation number 3. This only is called the ideal gas equation. So for all ideal gases where mu is the number of moles, the product of pressure into volume is equal to mu times R into T. So the value of R, the gas constant, is found to be 8.314 joule per mole per Kelvin. For 1 mole, for 1 Kelvin, this is the value. Understand? So if mu is equal to 1, for 1 mole of the gas itself, if mu is equal to 1, what? PV is equal to RT. Is it not? So how we have derived the ideal gas equation? We started from Boyle's law. Boyle's law states that at constant temperature, certain volume of the gas is inversely proportional to the pressure acting on it. And from Charles' law, at constant pressure, certain volume of a gas is directly proportional to the absolute temperature. So combining Boyle's law and Charles' law, we have derived a PV is proportional to T. PV is equal to a constant times T, and we express the constant in terms of the number of particles or molecules, and we derived PV is equal to Nk into T. Then the number of molecules is expressed in terms of Avogadro number and number of moles. So finally we have arrived at the ideal gas equation. PV is equal to mu into R into T. I hope you must have understood well. Fine.